Okay, so I wanted to do a quick mini lecture to talk about some more titration theory, just to clear it up. And I want to be really simple in this one from a computational standpoint to try to solidify some concepts for each of you all. So whenever we're talking about acids and bases, particularly titrations, the general definition involves an acid being added to a base or a base being added to an acid. When you add an acid to a base, we should know from our general chemistry 1, that is called a neutralization reaction. It's called neutralization because the base gains the proton generally and the acid loses the proton, and they are both now what we consider neutral because they are both no longer necessarily that form that you originally put them in. Now, in each of these cases, I've shown the generic situation of an acid, HA, added to a base, hydroxide in this case, which leads to water formation and a conjugate base, in this case, A minus. Remember, A minus is the conjugate base in this case. Now, let's say we added a base, to an acid. These are labeled incorrectly, sorry. This is base added to an acid. This is acid added to a base, excuse me. Acid added to a base B donates a proton, allows then for the conjugate acid using that base to be formed and the conjugate base formed from the acid. Both of these are your generic format of any acid-base titration. Remember, we still have to determine if it's a strong or a strong weak, but the generic form of these is going to generally be the same. Now, why do we care about this particular reaction? Well, we care about this particular reaction because in titration theory, we believe, even though we know acid-base equilibrium is happening all the time, we treat this as if this is what goes on first. As soon as we start the titration, this is what is dictating the number of moles that are left once our titration is over. Essentially, once we've added all that we want to add. So I wanted to make a broad kind of rule set of when to do what in a titration example. We want to be using moles when we need to find out how much analyte is left. The main purpose for titration is to find an unknown, find out how much analyte is left, find out the makeup of the solution. We need to use moles to do that because moles is the universal unit when we're dealing with stoichiometry. When do we use molarity? We use molarity when we're determining pH. We may or may not use Ka. So that means we may or may not use the ice table. We are not necessarily putting moles in the ice table. I usually wait and put molarity in the ice table after we have used the moles to determine it. Okay, so let's give you a simple, try to do a very basic example of a situation like this. We'll use this one, for example, first, and I'll use an actual reaction, an actual titration. Let's say that we were titrating HCl with sodium hydroxide. Again, this is a titration. Why? Because we're adding a base to an acid. We should know that the resulting is sodium chloride, right? And in this case, I didn't show the cation, but here I am showing the cation. And here is our neutralization reaction in this same format. We could break this down even further and go with this to make it equivalent to this type of reaction. Okay. If I was to tell you, and I'll write that up here, if I was to tell you that you had a 1 liter, 1 molar solution of HCl titrated using a 0.5 molar solution of sodium hydroxide, and you added 250 milliliters of a 0.5 molar sodium hydroxide, and you wanted to know what is the pH. Okay, let's say that was what you were posed. You had 1 liters of 1 molar HCl, and you were titrating it using 250 milliliters of 0.5 sodium hydroxide. So, just as I have said in this generic rule, we can't do anything about acid-base equilibrium, which gives us pH. We can't do anything about that until first we know how many moles of everything we have left. So normally what I do is I determine the number of moles of each thing and find out how much has been neutralized and how much we have left. That can be done using the volumes and the molarities. How many moles of HCl do we have? We have 1 mole of HCl. How do we know that? 1 liter times 1 mole. Okay? 1 liter times 1 mole. How many moles of hydroxide do we have? 0.25 times 0.5. 0.25 times 0.5. So that's 0.125. We clearly have more acid than we have base. Therefore, what should we have left over? We should have left over only acid, because we're going to use up all the base. This is our limiting reagent. This goes back to General Chemistry 1. This is our limiting reagent. The stoichiometry here is 1:1. This is 1:1. We can subtract confidently, and that leaves us with 0.875 moles of HCl. And this is the number of moles left, right? This is the number of moles left. Now, to get pH, we need to start thinking about concentration. Molarity is what gives us pH. So to get any kind of pH, we have to be thinking concentration. We know number of moles. Again, to get concentration, we should know our units of concentration by the back of our hand by now. We need moles per liter. Be very careful and make sure that you realize that now that you have added something to something, the volumes are additive. We must find the sum of those volumes, and then we can determine number of liters. So we know number of moles, 0.875 moles. Number of liters is 1.250 liters. Therefore, our concentration of HCl will be 0.7. 0.7. Okay, still doesn't answer our question, but we're now in molarity. Now how do we determine pH? This is where you need to understand and know your content as it pertains to what is a strong acid, what is a weak acid, and we should know that HCl is a strong acid specifically, and a strong acid dissociates completely, so therefore HCl concentration is the concentration of H3O plus, which equals 0.7 molar, and pH again equals negative log of H3O plus, which equals 0.15. Again, titration. We worry about moles to find out how much we have left. We worry about concentration to determine a particular pH. Now, think about this. This is something to marinate on, and I'll let you answer this yourself. In a titration, one of the main points in the titration that we're interested in is the equivalence point. And based on this, are we at the equivalence point or not? Think about that as we move on to the next example. Okay, now let's look at an example of a weak acid titrated with a strong base. Let's look at an example of a weak acid titrated with strong base. And let's take a look at chlorous acid. That's fine. HClO2 plus hydroxide gives us ClO2 minus plus water. Okay? And let's say that we have a 0.1 molar, 1 liter of HClO2, and let's say here we titrate with 100 milliliters of 0.2 molar sodium hydroxide. Okay, so I've changed up some of the numbers. I'm not with whole numbers, but it's still simple, basic, easy to use numbers just for these examples. All right, again, titration added one to another. This is not acid-base equilibrium where we just have an acid in solution. This is acid-base titration. So first thing we need to determine is moles of analyte left. Determination of moles of analyte here tell us that there is 0.1 mole of HClO2. We know that from the volume and the molarity. What about moles of NaOH? Moles of hydroxide, 0.2 times 0.1 liters is 0.02 moles of hydroxide. Looking at this, we see 0.02 smaller than 0.1. We have excess acid still. This is the limiting reagent. That means that we end up with 0.08 moles of HClO2 left. This is what we have in solution after this amount has been titrated in. Okay. Again, when we're dealing with determining pH, which is what we want to know. We want to know pH at this point. We need concentration. We need concentration. To get concentration of our particular acid, we need moles over liter which is equal to 0.08 moles over, how many liters do we have? 1.1. The concentration of HClO2 is therefore 0.073. Okay, 0.073. We cannot assume that the concentration of hydronium is the same as this because this is a weak acid. And when we have a weak acid, we need to use a Ka ice or Henderson Hasselbach if we are before the equivalence point. So to go back to that point I made about can you determine whether it's at equivalence? Again, these are not the same. We're not at equivalence point. Therefore, since we're before equivalence point, we can shortcut the ice table here and use Henderson Hasselbach. We can use Henderson Hasselbach. But to use Henderson Hasselbach, remember, we need to know not only the concentration of HA, we need to know the concentration of the conjugate, which in this case is ClO2. And how do we get the concentration of the conjugate? We need moles of ClO2 that were formed, and that is up here. Technically, it's up here. How many moles of product we form is based on the limiting reagent, same as in General Chemistry 1. So we formed 0.02 moles of ClO2 during this titration. Therefore, the concentration of ClO is equal to 0.02 moles over 1.1 liters, and that is equal to 0.018 molar. Okay, from here we can use Henderson Hasselbach by using the Ka in our reference tables. If we notice the Ka for chlorous acid is here, 1.1 times 10 to the negative 2. And we can dump this into Henderson Hasselbach, and if we remember, the format of Henderson Hasselbach is pH is equal to pKa plus log A minus over HA. That means that pH is equal to negative log 1.1 times 10 to the 2, 10 to the negative 2, sorry, plus log 0.018 molar over 0.073 molar. Again, I got these numbers from here. pKa I got from reference table. And once we plug this in the calculator, at this point in our titration, we have determined the pH using this equation. And the pH is 1.35. So, titration theory, very straightforward how to solve for a titration that is before the endpoint. Both of these examples are before the endpoint, and we either use Ka in this case because it is a weak acid, or we go with the concentration if it is a strong acid. So that is what this video has done. I'm gonna add some videos for base titrations and some videos for at equivalence point. But again, until equivalence point, you can use Henderson Hasselbach to determine the pH at any point in the titration before equivalence.